So thank you for the invitation. So originally I thought maybe I would talk about Fyodorov-Yarek heating, but I thought Louis-Pierre is here, Paul is here, they will surely talk about this, and then they're not talking, so I am talking about this. But this is actually related to the topic of the workshop, so it will be a very arithmetic topic initially. It will become a little bit dynamical, and then when we get into the proofs, you will actually start seeing connections with actually random multiplicative functions. And maybe the moral of my talk is that random multiplicative functions actually have arithmetic applications, and they have applications to the Langlands program. So this redeems random multiplicative functions. Okay, so so the topic is actually points on the sphere. So this another result due to Legendre. It basically says when you can write an integer as a sum of 3 squares. And this is actually a pretty deep topic. There's a lot of structure here. And to understand the talk, I actually need to tell you about the proof, because this will actually exhibit the role of the class group, the connection of the class group and quadratic imaginary fields to counting those solutions. So, okay, how do you actually generate solutions? So instead of asking for integers, you might ask for rational numbers. And in that case, you can actually use the local global principle, Hasse-Minkowski, to show that any integer n can be written as the sum of 3 rational numbers. And here you just need to check that this is doable mod p for every p and in the real numbers. So you know that there are solutions with rational numbers. And now what we want to do, we want to upgrade these rational solutions to integer solutions. So this is how quaternions come into play. We take these rational numbers and we define a quaternion out of them. And this quaternion has the property that if you square it, you get minus d. So now what are we going to do is that if you look at this, if you adjoin this quaternion to the ring of integers, you get something that's finitely generated. And it's going to be finitely generated in this extension, this kind of ring of quaternions. And now this is kind of a fact from algebra that this is actually an Euclidean domain, and there is a result that I call abstract nonsense, that any finitely generated subring of BQ is conjugate to a subring of BZ. And that's actually the main workhorse of upgrading rational solutions to integer solutions, because this Zx is finitely generated subring of BQ. So this means that there exists a Q such that it's actually, if I conjugate by Q, it's in BZ. So the point is that if I take my quaternion with rational solution and I conjugate it, I can get something in BZ, so something with integer entries. And now the point is that this y depends only on ijk. All the entries are integers, and the norm is actually minus d, because the norm of this and the norm of this cancels, and you just get the norm of x, which is minus d. So you actually used this embedding into quaternions. So you see, I took a rational solution, I created a quaternion, I got x squared minus d, and then I used basically, I call this abstract nonsense, to actually generate an integral solution. Okay, so we found an integer solution. If we have a rational solution, I can actually get an integer solution. But this proof actually tells us something much more interesting. And this is actually the important point. The important point is that it gives an action of the class group on the set of solutions. So if I have one solution, I can get more solutions in the integers. And this will be something that will keep reappearing throughout my talk. So I thought it makes sense to actually explain it. So I'll give even fewer details here, but let's imagine that I have a solution to d equals to a squared plus b squared plus c squared. So I start by constructing a quaternion out of it. This has the property that x squared is minus d. And now what this means is that I can formally embed this number field into qx, because I can just take square root minus d into x, because they both have the same property that when I square them, I get minus d. So now I can think of this number field as embedded in BQ. And in particular, I can pick an ideal of the ring of integers. I can consider a left ideal, which is BZ, and on the right with, then with IX of the ideal. Then again, by abstract nonsense, I know it will be BZ of Q. And then the point is that this guy, Qx Q minus 1, is going to be a quaternion and will give me another solution to this equation. So this is the mechanism through which the action of the ideals gives you new solutions. Okay, so does this make sense? So basically my point is maybe not the specific proof, but there is this connection between solutions to, this equation of 3 squares equals to d, and the class group of z of square root minus d, which allows you to take one solution and then get another solution. So there's an action of this class group on the set of solutions to this equation. And so this class group will keep reappearing throughout my talk. So what is the class group is the set of ideals modulo principal ideals. But basically you can think ideals to an approximation. Okay. So really this is the important point, that there is an action of ideals on the set of integral solutions to this equation. And now when you're aware of this, some things become less surprising. So for example, Gauss proved that the number of such solutions is the size of the class group times a constant, and this becomes much less mysterious once you understand that there's an action of this class group on the set of solutions. Okay, so this is kind of the situation up to Gauss. And the next actual step is taken by Linnik in the 1950s. So it's a gap of basically 100 years. And Linnik asks the very interesting question, let's not just count solutions, let's actually describe where the solutions are geometrically. So what Linnik wants to do is that he takes this set of solutions to x squared plus y squared plus z squared equals to d, and he asks where do the solutions lie on the sphere. So to do this, he needs to actually rescale everything by square root d, so that the points lie on the unit sphere. And then since the number of points is going to go to infinity, these points will become, denser on the sphere. And you ask, how do they actually distribute? And what Linnik shows, he shows that these points equidistribute with respect to Lebesgue measure on the unit sphere, on the 3-dimensional unit sphere. And he proves this along square-free integers d that are not congruent to 7 mod 8. That is necessary just to have solutions. But he adds this condition that d is congruent to 1 mod 5. And this condition, d congruent to 1 mod 5, is going to become a major irritant in the whole theory. So it seems like a very benign thing until you actually look at his proof. So where does this condition d congruent to 1 mod 5 come from? It comes from the fact that when d is congruent to 1 mod 5, 5 splits in q square root minus d. This means that if I take 5, I can factor it as 2 other primes in this number field. And so in particular, then I can use this ideal P to kind of generate other solutions out of it. So I have some kind of way of acting on solutions. If I had no split prime, I wouldn't have any way to connect the solutions. And then the method wouldn't work, yeah? No, it's not special. Yeah, that's right. Exactly. And this actually, I will emphasize on the next slide, actually. So this is somehow anticipating me. So that's actually exactly what Hendrik was saying. So this condition that d is congruent to 1 mod 5 can be replaced by a condition of the following sort. Pick a large integer m, then the solutions equidistribute along a sequence of d for which there exists a prime p less than m that splits. So you just need one. But the thing that cannot happen is that it cannot kind of drift off to infinity with d. The method of Linnik is not equipped with dealing with that. And so, yeah, it has to be fixed, exactly. And so this actually means that if you use this approach of Linnik, you're never going to cover 100% of the integers d. Because each condition that p splits in q square root minus d induces condition that D is in a arithmetic progression. So somehow you never, even if you intersect, if you take the union of arithmetic progressions, as long as it's up to M, you never cover everything. You're always away. Okay, and maybe just to kind of say what the Riemann hypothesis tells you, the Riemann hypothesis tells you that there's always a split prime up to size log square D, and the truth should be something like log D log D, based on probabilistic reasoning. And unconditional knowledge is D to the C, for some constant C positive. So that's the situation, but in any case, all of this is useless for application to Linnik, because his M is fixed. Okay, so this is about equidistribution of integer points on the sphere. And there is a completely parallel version of Duke's theorem, which has to do with Heegner points. And this is something that's not immediate, so I will describe actually what are Heegner points and how the story is similar. So Linnik theorem has this analog for equidistribution of Heegner points. Heegner points is just a fancy name for quadratic solutions to quadratic equations. So it's just a plus b square root of minus d over 2c, where b square minus 4ac is d. That's all. So those are the Heegner points. And you can place these points in the upper half plane. And you think of this upper half plane as a hyperbolic space. So you equip it with this volume element, so it stretches at the bottom. Okay, and then one other thing that you can do is that you can identify all the points in this upper half plane, which you can relate by a Mobius transformation of this type. Okay, and this gives you the fundamental domain if you map everything into a unique domain in which points can be mapped uniquely through this relation. Okay, so now you see we kind of get the fundamental domain looks like this. I have a point here, it's going to get mapped here. Okay, and I'm asking what is the distribution? Sorry? Z is X, Z is... Yes, this is a habit. Okay. So how do you think, okay, this is a strange thing. How do you think about this? So I think of this as the analog of taking the real line. The real line is like the analog of the upper half plane. And then you think of Mobius transformation as being analogous to this, translation by integers. And then you think of the fundamental domain as analogous to the unit interval. So you can think of this weird concoction here as some kind of hyperbolic generalization of this trivial thing here. But the main point is that on both spaces you can expand in eigenfunctions of Laplacian that have some arithmetic meaning. Okay. And why do we care about Heegner points? So the fundamental domain has an algebraic structure, is the moduli space of elliptic curve. So each point in the fundamental domain you can associate to an elliptic curve. And then the Heegner points are associated to elliptic curves with complex multiplication. And this means that these are elliptic curves that have additional structure. So this is what makes actually Heegner points distinguished and why we care about them. And now kind of there's a bit more to the story. So you can also, if you take an ideal I in Z of square root minus D, there's also a way of acting with this ideal on a Heegner point. So if you take an ideal, you can move the Heegner point to another Heegner point. Okay. So now the analog of Linnik's theorem shows that this set of Heegner points equidistributes as D goes to infinity. So roughly speaking, oh sorry, there's a typo. It should be B square minus 4AC. So you have basically also about square root D such points in the fundamental domain. And Linnik shows, I think with a very similar method, I assume, that this set of points equidistributes with respect to this hyperbolic volume element as D goes to infinity, but also with the congruence condition that D is congruent to 1 mod 5. And this congruence condition arises for the same reason that you need one prime which is split in the number field. Okay, and then so you see that this condition looks benign, but then when you understand the proof, you understand that this is a really serious thing to remove, that you would like to remove to understand this phenomenon better. And Linnik's method, I think initially was completely original. He called it ergodic method, but it was not ergodic theory. It was just spread, the word meaning that things spread. And then people managed to recast it as actual ergodic theory way later. Okay, and so in the 90s, this congruence condition was actually removed finally. And it was removed because people established an analytic approach to the whole problem. And this is kind of using a lot of heavy machinery, but here's maybe a kind of summary of the idea. So the idea is that you're going to, since it's an analytic approach, if you want to establish a equidistribution of points on the sphere, you can expand in a basis of spherical harmonics. And so these are Legendre polynomials. But you can, I mean, Legendre polynomials have many bases because they have multiplicity. And there exists, in fact, a special distinguished basis in which something amazing happens. So if you sum all these solutions to rational points on the sphere, rescaled by square root d, with respect to the spherical harmonic in a suitable basis, then the square of this is actually related to modular forms and L functions. So this is a form of the Jacques-Langlands correspondence. And the formula is basically this with some factor that I don't write down. But essentially it's this, it's an exact formula. And the formula says that there is this basis of spherical harmonics where the square of this is associated to a modular form of, I think, some weight and some level, maybe 8. And this modular form is twisted by a quadratic character d, and that's the same d as here. Okay, and so what is a modular form? Well, it's just a function that lives on this fundamental domain and which has a Fourier expansion. That's actually all you need to know. There is a Fourier expansion for it. And this object is basically taking the coefficients of the modular form, multiplying them by the Kronecker symbol, and dividing by n to the s. I think you're right, yeah. Something like that, yeah. So these notes are written on a train, so I cannot guarantee the full accuracy of... sometimes some things are just my memory, and my memory can be faulty. But I think you're right. It's excuse, yeah. But, okay. But I would say many people have struggled with this. I mean, kind of finding the exact relationship is not easy. Okay. So now, okay, how does this approach look? So I have about square root d points here. So the trivial bound is d for this expression. If I can get a non-trivial bound, I get equidistribution of points on the sphere. And so we have this relationship. And as you can imagine, the trivial bound for this is going to be exactly square root d. It's going to be disappointing. You get nothing for nothing. And this bound is trivial because you obtain it by just using the functional equation and then using complex analysis. And this is called the convexity bound because you prove this bound using convexity results in complex analysis. But basically, out of nothing, you get nothing. And then this was, so you see, if I plug this bound, I basically get nothing. Because I have square root d, I need to beat d. Okay, so in fact, what we want to achieve, we want to obtain a bound of this type for some delta. And this was first proved by Henrik in the 1980s. From what I heard, it was a time when people were skeptical of subconvexity bound. And they were asking you, what is the point? No? Okay. Okay, okay. Okay, that's what Peter told me. but okay. Okay. But in fact, there was a point. And then, okay, so later this actually, I mean, this theorem about equidistribution of points on the sphere and Heegner points actually goes by the name of Duke theorem, but it was also proven by Fomenko-Golubeva, and it actually, the main arithmetic input is actually the subconvex bound. So it's kind of a weird status regarding attributions, in my view. So now it's kind of an interesting thing, at least historically, and this is going to be relevant for the talk. Linnik actually claimed a much stronger result, which nobody mentions. And I think if people talked about this result more, maybe the whole research program would not be pursued. So what Linnik actually claimed is that he has a version of his theorem where he does not need a congruence condition. He actually just needs non-vanishing of LSKD close to 1. So so this is actually kind of interesting because we checked the literature. He really made this claim in Russian. Yeah, in Russian he made this claim, but he said my proof is right. I don't know, right. So it's kind of an interesting thing because he actually claimed this in Russian. He said my proof is very difficult. Then his student proved this with 1 over square root log d, and then so Malishev, and then Michel and Venkatesh claimed it with log d. And nobody knows why it's log d that they claim. So, but this comes from them, this log d. Yeah, I see. And what is the point of this condition? The point of this condition is that the number of exceptions, the number of d's for which this doesn't hold is really tiny. It's essentially almost big O of 1. I mean, it's really exponential of psi of d, but it's almost like big O of 1. Okay, so it actually gives you very, very few exceptions. Very few exceptional discriminants for which this does not hold. And I think if this was actually known as Linnik's theorem, maybe we wouldn't care about removing the congruence condition, right? We would care about proving no Siegel zeros. So this was a big error, you know. Yeah, okay, so this is what I meant, that Linnik actually never published the details. He backtracked. Then his student published a result with this condition. And I mention this because this is going to be relevant soon. Because in a sense, what we're going to do, we are going to recover his approach, but in a harder setting. And okay, and with an analytic method on top of it. Okay, so this was kind of the past. And now what is the current research in this area? So one kind of, the current research is actually about simultaneous generalizations. And the famous example here is something known as the mixing conjecture of Michel and Venkatesh. And so what this conjecture asks about, it says, let's take a Heegner point and let's take another Heegner point, right? And then, okay, if you just took a tuple of the same Heegner point, nothing interesting will happen. But what they do, they take any ideal and they perturb the first Heegner point by the ideal. And then they ask, does this set of pairs equidistribute in the product of two fundamental domains? Does this make sense to some extent? So it's somehow like, well, I'm looking at you, but I'm generally asking the audience, because if it doesn't make sense for you, it is over. So okay, okay, so it's kind of the point. The point is that Duke's theorem tells you equidistribution of this. Duke's theorem tells you equidistribution of this, just a change of variable. What about this, where they chained? So it's kind of like a diagonal thin subset in a fat space. Okay, so what happens? You take a z and you perturb the same z, but by a fixed ideal class, and you allow this ideal class to kind of go to infinity with d. So in a sense, you pick a sequence of d going to infinity, then you pick a sequence of ideal classes also going to infinity in a sense, and once you have fixed them, you ask about the equidistribution of z and the z acted by the ideal class in fundamental domains. So it's kind of like a thin subset. How does it equidistribute? No. Agreed. It cannot be any class, yeah. So there is a condition here. You see that is the minimal norm of any integral ideal representing the class approaches infinity. There is a condition on this ideal class that in a sense it also has to go to infinity. Okay.
Can you randomize sigma d and
well, okay, I'll tell you what is known actually soon. But yeah, you could, actually, I think nobody looked at randomizing, but if you randomize, maybe you can do it. Though I don't know a result. Actually, that would be interesting, so, but nobody randomized so far. So what is the situation? So this is actually interesting conjecture because there is this famous Andre-Oort conjecture, which actually asserts something much more modest. Andre-Oort conjecture asserts that this set of pairs is Zariski dense. But here we are actually making the stronger statement of equidistribution. But the Andre-Oort is much more general and is also known. But the mixing conjecture is not known. It remains open. So, okay, so what is, okay, here is a result of Kayutin on the mixing conjecture. So he proves that it's actually true along the sequence of fundamental discriminants, for which we have no Siegel 0, and for which 5 and 11 splits. So he needs 2 primes because there are 2 copies of the fundamental domain. So we need to act twice. Okay. And so as usual, this condition 511 I can replace by a condition that there exists 2 primes less than 1000, which are distinct. So essentially this condition can cover 99% of the discriminants. And this condition we are okay with, because I think there's not much we can do about it. So far, yeah, so far. So this is actually the best result towards the mixing conjecture. And the proof uses results from ergodic theory, so Einsiedler and Linderstrauss. And this is like a big black box that he applies. He gets that there's only a few limiting measures that can arise. And then one of them is the Liouville measure, which is what he wants. And then everything else is a measure that says that points concentrate on some thin subset. And to get rid of those possibilities, he uses the famous Schuh's bound from Anatomy of Integers. So it's kind of an interesting proof because heavy machinery and then something very classical to rule out other measures. Okay, so here's another example of a result in this kind of research program. This is actually what we're gonna focus about. So this is a result of Aka, Einsiedler, and Shapira, also using ergodic methods. And to state this result, I need to tell you what is the shape of a lattice. So roughly speaking, if I take a solution, if I take a point on the sphere, I can think of this point as a vector, pointing in one direction. And then I can take the tangent plane to the sphere and that vector. So that corresponds to my z intersection with v perpendicular. And then that gives me a lattice. So each time that I have a rational point, I have a vector, and then I have a lattice, which is orthogonal to it. Then I can take this lattice, I can dilate, rotate it, I can make it unimodular, and I can make it lie in R2. And then that is the shape of that lattice, roughly speaking. So now you can ask, now that you have this shape of the lattice, you can also identify it with a point in the fundamental domain. And now you have this nice thing, that one version of Duke theorem tells you that points equidistribute on the sphere. Another version of Duke theorem tells you that shapes equidistribute. Can you show that both equidistribute? Right, that's the question. And so this is actually what they show. So this is the result. Simultaneously, yeah. So they show that if you look at the positions of the points and the shapes of the orthogonal lattices, they simultaneously equidistribute. But again, along 1 mod 5, because they need this split prime to act on things. Okay, and so you can think of the mixing conjecture as some kind of simultaneous equidistribution in h times h. You can think of this as simultaneous equidistribution in PB times h, where PB is a quaternion algebra and h is the hyperbolic space. And then there's another theorem that I don't want to bother stating for PB times PB. But also something nice about 2 spheres. Does this make sense, this statement? So this is, okay, I'm coming to my main result finally after half an hour. But, okay, so all these results rely on dynamics. And so there is this program that was started by Blomer and Brumley, and this is also part of my research program that I will explain. The program is to develop analytic methods, not use dynamics. And this is also my personal research program. Let's try to get rid of dynamics and find analytic methods. So in a sense, as I like to say, let's try to take their toys away from them, to which they react very negatively, in fact, as I found out. So, so, but I think it's interesting because I think actually this dynamical method they definitely do something interesting, and I want to understand what is the actual analytic content of these dynamical methods. So what Blomer and Brumley want to do, they really want to develop a purely analytic automorphic approach. So no measure classification, just straight analytic. So here is kind of maybe our best achievement so far in this direction, which we're quite happy with. So we take this result of Aka, Einsiedler, Shapira about joint equidistribution of solutions on the sphere and shapes, and we can actually prove equidistribution just with this condition. Yeah. Yes, 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 but train. So, so the point is this, that they had a condition on the congruence condition, and they didn't have a Siegel zero condition. We replace their congruence condition by a no Siegel zero condition. And if you think about it, this is exactly the analog of this unpublished Linnik theorem, but in the case of simultaneous equidistribution. So we kind of recover this unpublished proof, but we recover it with a different method that Linnik did not intend. Okay. So in a sense, this is just as valid as natural as the theorem with the congruence condition. It's also really should be called Linnik's theorem. Okay, but the nice thing is that we don't use any ergodic ideas at all. And one thing that you get out of this is that the proportion of exceptional moduli is very small. It's like just E of psi of D for any psi going to infinity. So in fact, if you just care about equidistribution up to, let's say, epsilon, then we can prove that the number of exceptions is big O of 1, depending on epsilon. Okay, and then I also one more comment that this no Siegel zero condition could be replaced just by this. You just need enough split primes. So there is something funny you see for the first method of Linnik. You need one split prime less than 1000. For us, we don't insist that it has to be less than 1000. It can be anywhere, but you need enough. You need enough going to infinity. Okay. And one big difference is that it's not always true that you can find a split prime less than m, but this is always true. At least GRH implies it. Okay. So, okay, now I'm going to go into the proof. And you will see actually the emergence of probabilistic ideas in this. So we're going to hit RMFs towards the end of the talk. So, okay, so this is where it's going to get a bit more technical. So I'm going to first explain how we get to automorphic forms at all, to L functions and so on. So in the case of the mixing conjecture, what you're really studying is an expression of this type. You have one test function on Z, you have another test function on sigma d of Z, on the Z dilated by sigma d. And you want to show that this converges to the integral, the product of the integrals of phi1 and phi2. So here, this is the set of Heegner points, and then sigma d is just ideal class that acts on the Heegner points. And these are SL2 automorphic functions, so they're invariant under SL2Z. So one thing that you can do, which wasn't obvious to me, but you can actually just apply Plancherel on the set of chi, on the set of characters chi. So the first transformation is that you can apply Plancherel, and you transform this expression into something of this following type, where this is a form of Fourier transform of this test function with respect to the character chi evaluated at the ideal class associated to the Heegner point Z. Okay, so this is the first opening move of this. And then what we can do next is that we can spectrally expand phi1 and phi2 into Cas forms and Eisenstein series. So this is kind of, I think this is for the experts, these are actually kind of standard maneuvers. Plancherel, spectral expansion, that's it. So you kind of go on the Fourier side as much as you can. So you can now expand each of these phi into Cas forms, and there's some Eisenstein spectrum that I hide. And one kind of canonical problem that you end up having to do is bounding this expression, where this is a Cas form, this is a Cas form, this is a Fourier transform with respect to chi, and then there's this oscillation here, which is very important. And we want to show that this is little O of 1. That's the goal. So now the kind of idea here is that we have no way. What happened? So we need help. Okay. So you have no way of capturing these cancellations. So this is an idea that goes back to the student of Hendrik, in fact, Roman, in his QE approach. He just put absolute values, something you're never supposed to do because that's supposed to be always bad. So his approach is to actually just put absolute values. And why does this approach have any chance of working? Well, it has a chance of working if the L1 norm is small. You actually know that the L2 norm is of size 1, but the approach relies on the fact that actually the L1 norm is smaller than the L2 norm. And then it wants to use independence of Ui and Uj. So Sato-Tate type of thing, yeah. So this is the approach. We actually want to bound this. We get rid of oscillations. And so then there is this result of Valls-Purget that actually relates this Fourier transform to, again, L functions. So we are back into friendly territory with exponents 1/2. And now you can use heuristics from random matrix theory to know that this is generically little O of 1. So this approach actually has to work. And this strategy is going to fail if Ui is equal to Uj. But notice the following thing. We actually prove a theorem which is quaternion algebras times hyperbolic space, and their spectrum does not coincide. So thanks to this, we are always away from this case. If we try to prove the mixing conjecture, then this can arise, and then we cannot do it. We cannot do the diagonal situation. Okay, of course, I explained to you the plan of attack for the mixing conjecture, H times H. But if you do the kind of sphere times hyperbolic plane, it's actually very similar, just a bit more technical. And the point is that when it's quaternion algebras times hyperbolic plane, the spectrums are always different. So you actually never hit this situation that cannot be handled. Okay, so actually this is what I was saying, that when the groups are different, the spectral expansions are different, so we avoid this diagonal case. So in the dynamical setting, there is also a kind of instance of this. When you look at PB times H, there's only one invariant measure, the Radziwill measure, which is why the theorem is actually easy. But when you look at H times H, there are many possible limiting measures, and that makes it harder. That's why kind of Kayutin's result is regarded as deeper than this Aka and Shapira and Einsiedler. Okay. So now I want to actually tell you how we deal with this sum. So in the PB case, we only have holomorphic forms. For H, we have mass forms and Eisenstein series. So I will just work with incomplete Eisenstein series. So this is roughly what we actually end up having to bound. We have to bound something that looks like this. And we have to bound something that looks like this, and there should be a 1/2 here. Those are the two expressions that we need to bound. And there's also this issue that one character sometimes has a 2 in it. So this is a technical issue that I really don't want to get into, but we have that situation. And here, notice, so this is the analog of an incomplete Eisenstein series. And this is actually a random multiplicative function, because this is actually the sum of chi's in the subconvex range. So this is an RMF. And the useful observation is that RMFs are little O of 1 in L1 norm. So we're not going to use this now, but I just bring attention that RMFs appear in automorphic forms. Okay, so this is what we need to bound. So I'm just going to start with this first expression. Is this still making sense? Not really. L function, comma, chi. Ah, what is this? So this is just the L function of this class group character. Sorry? On ideals. Yeah. Well, this is summing over all ideals of z square root minus d. Yeah. Yes. No. Yeah, I should. Yeah. Maybe I should have like written something with a number field here, but yeah. No, this is an L function summing over all ideals of z. Okay. 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 So we have. Okay. How do we handle these expressions? So now I'm going into the proof. And so when Blomer and Brumley contacted me, it looked like this is going to be a very boring project where we're just going to iterate some ideas that I had with sound a long time ago, but it turned out much more exciting, thankfully. So let me start with the boring case. So the boring case is two cast forms. So we have to bound f times g, and there's a typo, there's a 1/2. And so the bound that we managed to achieve is actually this expression here. So f1g could be actually a mass form, something to keep in mind. And how does the proof go? So I will be pretty short here, but the rough idea is this thing that we develop with sound. So you can take L12 chi to the 1/2, Lg to the 1/2, and you can insert an exponential of a Dirichlet polynomial. And you can do that, well, trivially you can do that. And what you would like to do, you would like to then Cauchy-Schwarz on the guys on the left and the guys on the right. And then what you would like to do, you would like to expand this exponential into an infinite Taylor series, except that then you get an infinite Dirichlet polynomial, so you cannot evaluate it. But what we did in our method is that we developed a technique that you can essentially work as if you had exponentials, and you ended up with finite Dirichlet polynomials here. So we have a kind of technique that allows us to pretend that this exponential is actually truncated at a certain point, which is computable point, which allows for computation. It's a bit like Brumley. Yeah. Yeah, that's right. But the vanishing is not important for us. We're actually trying to bound the size, so we're not even, right? Yeah. So basically, the idea is that usually P is less than something like log D, and if P is less than log D, then this exponential can be cut at log D, because it becomes tiny afterwards anyway. So this is kind of the idea behind this. Yeah. That's right. That's not possible for standard modifier. Yeah, so we develop a different modifier where such a thing is possible. Okay, so this is kind of the idea of the proof. We Cauchy, then we get something, then we can compute. We get a twisted first moment, that's computable. Okay, and then we need to bound an expression of this type. So I'll be kind of quick here. So what we do is that we take this, we restrict to this subset. On this subset, it's at least eta square. And then I just do, well, triangle inequality. This is at least KDP equals 1 minus this. And now I expect this to be 1/2. I expect this to be eta, if eta is small enough, at least if I had satutate. The problem is that this could be a mass form, so I don't have satutate. So what happens is that there are two things. So first we need to show that if you have Siegel zeros, this is 1/2. And then we need to show that even without satutate, this is less than 1/2. No. This could be any mass form, and this is holomorphic. Yeah. Okay. So the first thing is actually showing that if you have no Siegel zero, the first thing is 1/2, and the second thing that we show is that even without satutate, you can show such a result, which is enough for the application, because then you get 1/2 minus 0.4999, and that's enough. And this 4.999 is actually not far from the truth, as it turns out. It's not far from the best that we can do. So here is okay. So there are two things. So first, there is this thing of showing that if you have no Siegel zeros, then you have this type of lower bound. So we always assume this is trivial, but then we get stuck on this for quite a long time. I don't know why, but so I'll just give the short proof. The short proof is basically this. It's enough to bound this expression. I put a smoothing. Thanks to the smoothing, I can truncate here. If you use a naive approach, you just have this term. But I can subtract this term because it's actually always small anyway. So I subtract it. And this term is kind of like normalizing this term. This is how I think of it. Because trivial bound for this is log d. But after you subtract this bound, you actually have a bound of a cubed, which is using the fact that the number of zeros in a over log d is at most a by a positivity argument. So then you can actually shift the contours, and here you get e to the minus psi, and here you get a cube. So you actually win. So this actually took a surprisingly long time, that's why I mentioned it. Okay, so now we want to... Yeah, that's right, yeah. So, okay, now we need this type of upper bound. And so, okay, now what we do, we would create a polynomial that will be of degree up to 8, and it will have the following properties. It will be always positive. The degrees will be up to 4, mixed. But if you want to go above 4, then the other degree has to be 0. The point for this is that this is the best that we can do in terms of functoriality and the scheme-Shahidi result. And then there's a constraint that the integral with respect to Tate measure is bigger than 1/2. And so if you have such a magical polynomial, the proof is very easy. You just take this, and you insert it as an upper bound, and then you just average, and you're done. Right? So instead of detecting bigger than epsilon, I'm going to actually just detect different, just to illustrate the argument. And the point is that this polynomial is bigger than 1 on the diagonal. So if they're equal, then this is -1. But on the other hand, it's also okay. It's also positive, right? So it's also always fine. Okay, let me see. Unless I'm botching. Okay, I'm afraid this is maybe a little bit. There's a little botching here because if they're equal, then this is actually okay. Yeah, okay, this is a little bit botched, right? But it should be, okay, it should be h, it should be not 1 minus, okay? And the other thing should be less than 1/2. Okay, just a few typos, sorry. Okay, so the point is that in the paper it is correct, but yeah, it doesn't matter. So it just like, it shouldn't be 1 minus, it should be just the thing, okay? Just the polynomial. It should be just h of lambda, and then this thing should be less than 1/2, okay? Those are just a few typos. And then it's correct. So, okay, and then so what we did is that we actually used linear programming. We found the polynomial. And you can inspect by hand that all the degrees are fine, right? On the diagonal, it's easy to check because you can just do it. But how do you prove positivity? So what we did, we wrote this as a sum of 30 squares. 30 squares of other polynomials with integer coefficients. Sorry? Yeah, no, but we wrote this as a sum of 30 squares. And this used like some kind of semi-definite programming, and we had to tweak by hand at the end, which was a bit unpleasant, but we had to do some tweaking. But anyway, this is the polynomial, and we actually, in the paper, we have the proof. And the proof is just 3 pages of us listing all the 30 polynomials, and that's it. So this is my favorite proof in the paper. So, okay, so then, yeah.
Experimental work.
Yeah.
Right? And how do you know we can make a combination that is not identical?
Okay. So we use first linear programming. We just took a grid of 100 by 100 point with all of our constraints. That found some polynomial. Then we use something called semi-definite programming to write that polynomial as a sum of squares. And then that thing actually had floating point errors. So then we had to do some tweaking by hand to do the rounding. Because you see, everything is an integer. So that was kind of done a bit by hand, the tweaking, the final tweaking. We didn't know. We had no clue. We had no clue. Just got lucky. No, because if you just include up to 4, it's not true. It's true if you include 6. But up to 4 is not true. It's not possible. So that's kind of, and this is close to optimal. So this actually gives you this upper bound 4914. This is basically optimal. You cannot do better with the constraint. Everything that we know. Everything that we know. We use, you see, up to 8. Yeah. No, unconditional. Yeah. Okay. So now there was this issue of bounding this guy. So this looks very similar. So you think, okay, I'm going to repeat the same proof. The problem is that when you try to repeat the same proof, you're actually not able to compute this. This actually runs into pretty difficult issues about class groups that we don't know how to solve. So we don't know how to actually compute this if you have a square. So we develop a method for getting cancellations without modifiers. So this is kind of maybe the most innovative part of this. So I'll show the technique. It's very easy. It's inspired by Turan-Kubilius inequality. So the idea is this. So I take a polynomial PG, which is this. And this has typical size. Well, actually, this is not the typical size. But let me define this type of mean view. And I'm going to define this kind of event, which is actually not a typical event. Okay, so I define these events. And now what we're going to do is that I'm going to bound the sum over chi not in t, and then I'll by the sum over chi in t. So let's see how this goes. So if chi is not in t, I'm going to do Cauchy-Schwarz here, right? And then when I do Cauchy-Schwarz here, this event t becomes typical. So if chi is not in t, then this is small. So what happens is that I can put, you see, my event t is that I am close to this mean mu, okay? And this is an atypical event without any weighting. But after I do Cauchy-Schwarz, with this weight, it becomes a typical event. So with this weight, chi not in t is not typical. So if I do Chebyshev, I get something small. I get actually a saving of 1 over mu. So now let's see the other case, when chi is in t, then I Cauchy on the other term, right? I Cauchy on the other term. And now what happens is that this event chi in t is atypical. Because t is uncorrelated, chi square is not really correlated with chi. But I can compute chi with chi square. I cannot compute chi square with chi. So there's like this asymmetry in the problem. And so then this means that if chi is in t, then it means that actually this is bigger than 1/2 mu. I put this, and this is small. Because these guys are uncorrelated. So this is actually typically of size square root of mu. So this is also 1 over mu. And this idea can be pushed. And I think you can actually kind of modify just by stratifying into level sets. So you don't need actually modifiers, which here, because here you cannot make it work with modifiers, which is kind of a weird thing. Okay, so, okay, and then finally there is the case of this incomplete Eisenstein series with a half. The same proof works, so I will kind of skip the details. And now we are kind of getting a bit more ambitious with Brumley and Blomer, and we want to attack the mixing conjecture. And if you attack the mixing conjecture, you have 2 incomplete Eisenstein series next to each other. And here we want to use this work of Harper, actually. Because work of Harper actually shows that this is little O of 1. Because this is a RMF. So we want to kind of use that work in the case of products of 2. But this is kind of a bit in progress, so I cannot really say. But to me, it was interesting that actually RMFs are really kind of useful. They are arithmetically, they seem to have truly arithmetic consequences. And but one kind of drawback is that if you want to use the method of Harper, we need to assume a strong zero-free region, because we need a lot of small split primes below exponential of square root of log d. So unfortunately, we won't be able to prove such a strong result with just no Siegel 0. It's also kind of weird. Okay, so So that's it. Thank you.